This is another classic momentum collision example, typical problem. But this time the emphasis is on elastic collisions, not inelastic collisions. And this is a continuation of the last problem, which was inelastic. Now we're saying, okay, what happens if we bounce these cars off of each other? The key feature, does anybody remember what was the distinguishing characteristic of elastic collisions, not inelastic collisions? You gotta be careful how you talk about the two. If you say like, what was a key feature in elastic collisions, then it sounds like you said the word inelastic. Sarah?
They trade velocities?
They can trade velocities. That's only true when the masses are the same. But that's a good rule if the masses are the same. Zeroff?
They don't lose momentum. They don't lose energy.
Yes, in particular, they don't lose kinetic energy, okay? So kinetic energy is conserved. That is the key distinguishing feature of elastic collisions. Kinetic energy is conserved for elastic collisions. So one way to approach this problem, and again, remember to just, pause, fast forward, rewind. I won't be offended. But the key, using this key feature, you might think, okay, I'm going to set up this big equation. And you can do it this way. We set up a big equation using kinetic energy like 1/2 mv squared, like 1/2 mva, va squared plus 1/2 mv, blah, blah, blah. And you just go on and you make this big ugly expression. But it turns out there's a much, much more elegant, easier way of doing this. And it's all based on something called relative speed, okay? And what I want to get across to you right now is that relative speed is a consequence. It's a corollary. It's a logical conclusion that you can prove from conservation of kinetic energy. So this is synonymous with saying kinetic energy is conserved. It turns out that if kinetic energy is conserved, step by step, here we go. This is the original velocity with a positive or negative for the first object. This is the original velocity with a positive or negative for the second object. This is the final velocity of the second object after the collision has occurred. This is the final velocity with a positive or negative of the second object after the collision occurred. This little dash does not mean to the first power. In fact, you could write this a different way if you want. You can write this with V2 final, V1 final if you want, okay? You can have that little subscript if you want, okay? But it's just a convention that I've seen and I've gotten used to it, so it's a habit of mine to use this little prime. It's a little apostrophe prime thing. This left side represents the speed of the approach, and this right side represents the speed of recession. Picture two cars going at each other. Two cars going at each other on the road. And if they are approaching each other, or even better, I'm going to make one catching up to the other. This is 12 meters per second. This is 3 meters per second. What is the speed at which, what is their speed of approach? What is the speed at which they are approaching each other?
None.
9 meters per second would be the speed of approach. And if you plug the numbers in, if you do 12 minus 3, or even if you do 3 minus 12, the relative speed is going to be 9. That's the speed of approach. If this were a 3 going the other direction, now their relative speed is what?
15.
15. You would put in a 12 minus a negative 3, which is 15. But here's the really interesting part. The really interesting part is that in E4, elastic collisions, this right side, this will equal. Like, I don't know exactly what they're going to be, but I know that it's going to be 15. They're going to actually going away from each other at 15 meters per second. I don't know precisely what each speed will be, but I know they will be going away from each other at 15 meters per second. So let's look at how that manifests algebraically. The two pass cars are approaching each other. I'm going to first set up the relative speed equation. V1 minus V2 equals V2 prime minus V1 prime. And let me make this, I'll do this whole thing and I'll make it a little bigger. Okay, let's go step by step. Here's my relative speed equation. I'm going to plug the numbers in from the problem. But all I have is information about the beginning. Positive 3 for A, negative 1 meter per second for B. Which, if I recall, aren't those the same numbers we used for the last example? But now the only difference is we're saying that that the collision is elastic. So this doesn't look very useful yet, but this is going to be enormously useful for the problem. And what I like to do is we're going to be doing algebra here, so we're going to be substituting this equation into another equation. So if you solve it for V sub B prime, VB prime, it's VA prime plus 4. Okay, fine. VB prime is VA prime plus 4. So let's plug that into this equation. So now I'm going to use conservation of momentum. Trust me, do all the red writing first. Every time you know there's a moving object, you write down an MV. You write down an MV. So moving object in the beginning, moving object in the beginning. In the end, again, two moving objects. Moving object in the end, after the collision. So I write a bunch of MVs, then I put sub A, sub A, sub B, sub B, sub A prime, sub B prime. Don't make the mistake of thinking, guys, this V sub A is not the same necessarily as this V sub A prime after the collision. This is just conservation of momentum. Total momentum before, total momentum after. Now I'm going to plug in like crazy, but I'm going to plug in that expression for VB prime. This right here will get plugged in for this expression. This variable for VD prime will have an expression in parentheses. So here we go. 0.25, positive 3, 0.5, negative 1. I don't know what VA prime is, but look what happens here. Your algebra instincts are kicking in, and you realize, look, we have only one unknown now. VA prime. We have only one unknown. Now we're going to plug, chug, and solve. Be careful. What do you have to do with this 0.5 outside these parentheses? Got to distribute that to the VA prime and to the 4. Very common mistake. Often the reason somebody doesn't get a relative speed elastic problem correct is they forgot to distribute. Also pay attention to negative signs. Plug, chug, crank it out, and you get negative 2.333 meters per second. And I have a very convenient way of getting VB prime. What is my convenient way of getting VB prime?
Add 4 to the end.
Just add 4, and what she's referring to is, let me move some things around. She's referring to the fact that we already have an expression set up for VB prime right here, just VA prime plus 4. So just plug back into that, and you get 1.67 meters per second. By the way, what is the relative speed between these two? Four meters per second. Are they moving toward each other or away from each other? Away from each other, because this is after the collision. By the way, what is the relative speed before the collision? 4 meters per second, because one is going to the right at 3 and one is going to the left at 1, and they are approaching each other at a relative speed of 4 meters per second. Incidentally, if I were to ask you to calculate the kinetic energy, here's the cool part. You put in these velocities, calculate the total kinetic energy at the end, you're going to get the same thing as the total kinetic energy in the beginning. And that's one way to prove to yourself that, hi Anna,
Hi.
filming a video right now, so hold on a second. So that's one way to prove to yourself that all this relative speed stuff really does come from the law of conservation, not the law of conservation of energy, but the fact that in elastic collisions, kinetic energy is conserved.